Hi, my name is Michael, and this is Adam, and today we are going to talk about latest advances in LLVM loop optimizations. I will start with our progress in loop unrolling, and Adam will talk about loop distribution and some other passes that we improved. So, what is loop unrolling? Loop unrolling is a well-known compiler transformation which just replicates loop body several times. And there are two types of loop unrolling. Partial loop unrolling, when after the transformation we still have the original loop. And complete or full loop unrolling, when the transformation entirely removes the loop. The latter case is the most interesting for us, and I will be talking mostly about it. So why do we want to unroll a loop, and what drawbacks could it have? First of all, when we replicate loop body as many times as loop iterates, we remove loop control flow, which is often enough to justify this transformation, but it's not the only benefit. On top of that, loop unrolling often enables later passes, including simple ones like constant propagation and dead code elimination, and sometimes even complicated ones like SLP vectorization. However, loop unrolling also has several important drawbacks that we should be aware of. First of all, when we replicate loop body several times, we of course increase code size. But increased code size means that later passes have to spend more time processing our code. And that means that compile time will also grow. But even if we don't care about code size and compile time, loop unrolling is not always a performance win. And the reason is that we can produce huge basic blocks, and later passes just might fail to efficiently deal with them. And even if they are able to do this, we can easily saturate hardware resources, like instruction cache. So it's not always a performance win. So how do we maximize our benefits and at the same time minimize the costs? In LLVM, we currently use very simple and naive heuristics for it. We only unroll tiny loops. But that makes us miss many optimization opportunities on bigger loops. So that's what we didn't like and wanted to fix this year. We introduced new heuristics which aimed especially for bigger loops. But as I said before, unrolling big loops is often expensive and sometimes even dangerous for performance. So we have to be extra careful with this. Some experiments showed that just removing loop control flow usually is not enough to get any performance from this. So actually we need to make sure that if we unroll the loop, we enable later passes. And so our new heuristics actually analyze the loop and tries to predict what outcomes can we expect from later passes if we do this. But what effects are we looking for? Let's quickly go through a simple example to see. So this is a constructed example, and we have just one loop, simple loop operating on two arrays. One of the arrays, in this case, B, is a constant, and we know all its values at compile time. So what happens if we unroll the loop? If we unroll the loop, all loads from B now has constant indexes. That means that we can substitute them with concrete values. So let's do this. When we did this, we now exposed even more optimizations. So we can fault all multiplications and then additions. And when we do this, we also make a lot of loads from A dead. So we can remove them as well. In the end, we will simplify everything to just one instruction. Of course, that's an artificial example, and it's constructed one just to demonstrate how powerful these effects could be. So the question now is, how can we distinguish such loops from the others? What do we do? How can we predict such outcomes from later passes? And to do this, we actually decided to teach compiler to simulate the loop. And we do this instruction by instruction, iteration by iteration. We visit every instruction and try to predict which simplification are possible on this. And if we find something, we record this information and use it when we visit the rest of instructions, because we can trigger simplifications on one instruction when we simplify the other. And along with that, we accumulate our estimates for costs of the original loop and unrolled loop. And we use these numbers later when we decide whether we want to unroll or not. So let's return to our example to see how it would work there. So we start on iteration 0 on the first instruction. This is IR-like representation, just a little bit simpler. So the first instruction is a load from B. And if we unroll the loop, I would be 0. So that means that we basically want to load the first element. And we know that this element is 1. So if we unroll the loop, this instruction would be simplified to 1. That basically means that this instruction has 0 cost for unrolled loop. But it's just a usual load for the original loop. So it has a cost of the load for original loop. So we add its cost to our estimates for original loop and add 0 to unrolled loop cost estimate. And then we proceed to the next instruction. Next instruction is another load, but now it's from A, which is not a constant. Even if we unroll this loop, we can simplify it. So this instruction contributes to both estimates, for both unrolled loop and original loop. Then we proceed to the next instruction. This instruction is multiply. But if we unroll the loop, we know that one of the operands is 1. We just figured out 2 lines above. And that means that in the unrolled version, this instruction would be also simplified, because multiply by 1 is just an op. So that means that we don't need this instruction in unrolled version. And again, it only contributes to original loop cost then. In a similar way, we proceed with the remaining instructions. So this addition would be simplified, this addition would be simplified, comparison would be simplified, and branch would be folded when we unroll the loop. So when we finished iteration 0, we proceed to next iteration, iteration 1. And we do the same stuff. So let's just fast forward it. So in this case, literally entire iteration turned out to be dead. So after it, we process the remaining iterations. So let's just skip it and jump to the end. In the end, we get pretty accurate estimates for costs of original loop and unrolled loop. So that allows us to estimate speed up that we can get from unrolling this loop, at least our estimate of it. So what do we do with this now? Let's see. First we want to check if we actually can unroll this loop without any analysis at all. So if this is tiny, we don't need this at all. And that's actually the first and the last step that we have before this new heuristics in LLVM. So if the loop is tiny, we unroll. Otherwise, we do not. But now we added a few steps to this logic. So instead of giving up on a loop, we next check if the loop is huge. And if it is huge, we give up on it. And the reason we don't want to deal with this is that even if we predict that we can remove 99% of instructions of a huge loop if we unroll it, even one remaining percent might be so big that we just can't handle it. We might fail even to compile it. So the interesting part is that if the loop is not tiny and is not huge, what to do now? At this point, we go to our estimates and see if predicted speedup is high enough for us to be convinced to unroll this loop. And currently, we just take relative speedup, like percentage of removed instructions, and compare it against some threshold. So, OK, it sounds good. But for now, we only looked at one simple constructed example. Let's see how it works on real test cases. First of all, it showed significant gains on some kernels, including convolution loop and some linear algebra computations. We observed up to 70% gains there. Also, we saw several improvements across different benchmark suits, including LLVM test suite and even one test in spec, 2006. At the same time, we didn't see any performance regressions, which is good, but there were several serious compile time regressions. So our next plans include investigating and fixing, or at least understanding, these compile time regressions. So let's take a quick look at what we are going to do next with this. So as I said, first of all, we need to fix these compile time regressions if we want to enable it by default, and we want to enable it by default. We need to understand that we can't avoid some compile time regressions, but if they are understood, it's fine. And if they lead to big performance wins. Another way we want to improve this is to model more optimizations, more future passes in our estimator. Currently, we only predict effects of basic simplifications like what int-simplify and simplify CFG would do. And there is also a Chandler's patch for estimating dead code elimination effect, which we think is very important for this to have. So we hope it will be committed soon, and that will make this framework even more powerful. Another way to exploit this new capability of compiler is to analyze loops with early exits and find their trip counts even if we failed to do so before. An example would be a string-len-like loop, which operates on a constant string. And if we're able to simulate it till the actual exit from it, we can rewrite this loop without early exit and hopefully by this enable later loop passes, even loop vectorizer maybe. That's all for unrolling for today. But unrolling was only one part in our efforts to improve loop advances in LLVM this year. So I'm inviting Adam to talk about other stuff. Thanks.
Did you guys hear it, or?
Yeah.
But should I repeat, or repeat? Repeat? OK. So approach. I'm going to first talk about the approach for the second half of the talk. So I'm going to cover new loop transformations. And I will also demonstrate these transformations on a case study of a real-world loop that inspired these transformations. Now, of course, the goal is not to hack this particular loop, but to build new general optimizations that apply to other cases as well. So with that in mind, let's jump to our case study. It's the Hammer benchmark from spec in 2006. Hammer is an open source package that's used to analyze gene sequences. So it's a pretty interesting package. And at the heart of this package, there's this loop. Now, don't worry reading it. I'm going to explain what it does by breaking it up a little bit. So the loop has I divided up the loop in into three sections. So let's look at the first here. If you look at this more carefully, what you see is that every single line here is writing the same array element, MC of k, basically conditionally refining its value. If you look at the middle section, it's similar in structure, but it's writing a different array, DC, or the array element DC of k. And if you look at the bottom part, it's writing yet another array, IC, or the element IC of k. So what we can notice at this point is that there's a certain level of independence between these different parts. So how can we optimize this loop? Can we vectorize it? Unfortunately, the answer is no. And for the reason why, we have to look at the middle section of the loop here. So let's look into the first instruction here. And then let's split the store on the left-hand side from the rest through a temporary. And then let's draw the data flow. So there's obviously data flow where we just split the two instructions. And then there is a loopy data flow because the value that we're storing in one iteration at the bottom store will be read by the subsequent iteration by the load on the top. Also notice that the flow is here through memory. Now let's look at the same thing with data dependencies. For the green, for the blue arrow, we have, this is a within one iteration dependence, so it's loop independent. Whereas the red one is between two different iterations of the loop, so it's loop dependent or loop carried. Also, this dependence is backward, lexically backward, of course. So it's basically this type of dependencies are called loop carried lexical backward dependencies. And these are problematic because they can inhibit vectorization. Let's see why. So let's think about what vectorization does. Vectorization will coalesce multiple adjacent iterations of the loop into a new vector iteration. So let's demonstrate that. So let's take one iteration of this. Let's duplicate it into another iteration. Let's adjust the bottom iteration to be really the next one, so k plus 1. Now let's draw the loopy data flow. So this is straight now, obviously, because we have two iterations represented here. But this is not how vectorization would actually merge the two iterations, like after each other. What it really does, it really overlays one on top of the other, more like this. And then it takes the same instruction for multiple iterations, like these two, and then combines it into their vector counterpart. But let's see what happened to the data flow here. So now it's broken because it's pointing against program flow. So backward dependencies like this don't play nicely with vectorization. So let's look at what that means for our loop. So let's put the, which way? Oops, sorry. Okay, let's put these back together, like before we split it. So we have the backward dependence there. Now let's look at the entire middle section of the loop. Now, as it turns out, that there are two more lexical backward dependencies like this in this section. And because of this, this middle section of the loop is non-vectorizable. On the other hand, the top part, in terms of memory dependencies, is vectorizable. Let's also look at the final third part to complete the picture. So if you look at this, turns out this is not vectorizable either, because this if block here is not if convertible, because the condition depends on the induction variable, and this is not something we support in the vectorizer currently. So to summarize the loop, the top part is vectorizable, the bottom part is non-vectorizable. So how could we take advantage of the vectorizability of the top loop and still optimize this loop? So one technique to deal with this would be to lexically split this loop into two loops at the green line like this. And this is called loop distribution. So let's summarize our current plan. How are we going to optimize our case study loop? So we're going to distribute the loop, and then we're going to basically run the regular loop vectorizer after it and perform vectorization. So these two transformations together implement what we call partial loop vectorization, because we, at the end, obviously vectorize only part of the loop. So in order to support partial loop vectorization, like for such cases, we basically set out to implement the missing part out of this, which is the loop distribution pass. So loop distribution is a general optimization that's available in most other compilers. And let's review it a little bit by its advantages and its drawbacks. So as I said, if you have a loop, by splitting it up, you could enable optimization on the different parts, like partial loop factorization. But there's also another set of optimizations that you can have by splitting up a large loop into smaller loops, such that the new loops would fit the underlying hardware structures better. For example, the data caches. So if you think about, for example, in a large loop, you could have many different memory regions corresponding to arrays, for example, mapping onto the same sets in the cache. And if you run out of the number of ways, you will start thrashing, because you will start evicting useful work. Another example is really targeting the loop to the number of hardware prefetcher streams the hardware has. Another example outside of the caches is if you have a large loop, you have extensive register spilling. By splitting up the loop, you could remedy the situation, hopefully. Of course, on the cost side, you are going to be adding new loops. So there is new control transfer instructions and induction variable handling that's associated with that. Also, if you have multiple loops at the end that require the same computation, you'd have to duplicate those across the new loop. So there's obviously extra instructions at runtime that will cost you. Also, ILP could be reduced because you're going to basically be sequentializing the code by splitting it into loops, into multiple loops. So let's assume it's profitable to distribute. When is it actually legal? For that, we have to look at dependencies that are spanning across the distribution boundary, which is this green line here. So as I said, for scalar computations, we're going to duplicate computations if they're kind of if the dependency is spanning across a boundary. For memory dependencies of array accesses, forward dependencies like the blue arrow here is fine because we're going to execute the second loop after the first. On the other hand, lexical backward dependencies like the ones we covered would be legal for the very same reason. We also need to watch out for unknown dependencies. And these are the results of aliasing accesses within the loop. So the two pieces of analyses we need for this is loop dependence analysis to reason about the direction of the dependencies, and then collect runtime alias checks, if possible, for the loop. So these two analyses are actually related. They both look at memory accesses within the loop. Also, typically, client transformations are interested in looking at both. So it makes sense to have it in the same analysis. And this is what we implemented in a new analysis called loop access analysis. The name is pretty obvious, but it analyzes memory accesses within the loop. That's how we came up with the name. This code is not new. It was born from the loop vectorizer, which had its own dependence analysis framework and a runtime alias check collection code. But we have taken this code, generalized it to give you basically the full set of dependencies, and then packaged it as a new analysis pass. So as you expect from an analysis pass, it will on-demand compute the result for each loop and then cache it for later use. We also added a new transformation utility called loop versioning, which basically takes the runtime alias checks from loop access analysis and then performs the loop versioning transformations, which would enable the underlying transformation like distribution in this case. Now, if it's actually legal to distribute this loop, what is the algorithm we're using to perform the actual distribution? So it's intentionally a very lightweight algorithm in a sense that we didn't want to populate new analyses, but simply use those that are available. So loop access analysis is shared now with the vectorizer, so it gets basically populated either way. So we don't build a program dependence graph, and we don't build control dependence either. These would be new analyses. And also because we only target inner loops, because that's what loop access analysis supports. Because we don't have the full dependencies for the program, we had to modify the textbook algorithm a little bit. Basically, we don't perform reordering, just like the vectorizer doesn't perform reordering. For scalar computations, we can duplicate computations, but most importantly, for memory operations, we have to preserve the original order of instructions prior to distribution. So let me demonstrate this on a simple example. So consider this as the internal control flow of a loop. I omitted the loop back edge, and I don't have control transfer instructions either for simplicity. So in the first step of the algorithm, we're gonna linearize these instructions. And then suppose we have these backward dependencies and these forward dependencies. So in the next step, we're gonna partition these instructions, and partitions will at the end form the basis of the new loops we're gonna be creating. And the partition algorithm, initial partition algorithm, uses only memory operations, so we remove everything else, and only the backward dependencies. And the goal here is to isolate these backward dependencies into their own partition. So we create boundaries such that there's no edge spanning across the boundary. So we had one here and one here. So in the next step, we're going to start populating these partitions with all the instructions that are necessary for them. So first, we're going to look at the top partition, and the store depends on them all. So we add it to the first partition. That's it for the first partition. Then we move on to the second. Store depends on an add, so we add it. And then the add depends on a multiply, and which is already assigned to partition 1. So this is our duplication case. So we're going to duplicate this in the second partition, and then move on basically recursively visiting these nodes. And then finally, we finish partition 2 and move on to the bottom partition. So the store here depends on the mall, so we add it. And then the mall depends on the load. So if we were to duplicate this load, as we did with the mall, this would change the ordering against the instructions in between them. And as we said, for safety reasons, we can't do that. So what we do instead, we basically keep the original load at its place, and then just merge these two partitions. And then finally, we complete populating the bottom partition as well. So at this point, what we're going to do is clone the original loop to correspond to the new partitions, and then remove any instructions that was not assigned to the given partition corresponding to the loop. This could create empty basic blocks, which will let simplified GFD to clean up. Now let's see where this takes us with our case study. So we distributed the loop with the help of versioning. It has actually made aliasing accesses. And then we let the vectorizer vectorize the top loop for us. So this is what the loop looks like conceptually after these transformations. So split and the top vectorized. So we do we run this and we see nice instruction count reduction due to vectorization at the top. However, it does not completely transfer over to cycle count reduction as we were expecting. And the reason for that is that the original loop had a pretty long critical path. And now that critical path was pushed down into the bottom loop. And because we moved a bunch of instructions from this loop into the top, there are fewer instructions to overlap with, so it's getting more exposed. So let's look at this, this critical path. It involves the middle section that we've been looking at. And if we draw it, it looks like this. So at the top left, we start with the load, and we go through the add and the compare and some conditional moves, and finally arrive to the store, which will recur back to the load on the next iteration. So this is a pretty long critical path, and store-to-load forwarding helps here because hardware store-to-load forwarding helps here because the store at the bottom does not have to fully drain into the caches in order to unblock the load on the top. On the other hand, it still needs to reach certain execution stage to get into the store queue, and then the add would still have to wait for the latency of the load. So we could do something better in software, and we can short circuit this. We can basically take the stored value and then propagate it to the uses of the load, which is the add in this case. So something like this. All right, so that would definitely shorten the critical path. So how could we implement this? So if we go back to our code and then connect up the stores with the loads that they forward to, we have 1, 2, and 3. So this should look familiar. This is the exact same lexical backward dependencies we were looking at earlier. So this suggests that we could basically formulate loop-aware store-to-load forwarding using dependency analysis results that we already populated in loop access analysis. So we implemented this idea in a new pass called load-elimination. So the algorithm and it's called load-elimination because obviously as part of store-to-load forwarding, the load becomes redundant and can be eliminated. So the algorithm for this goes like this. It's very simple. So we look at loop carry dependencies with an iteration distance of 1. We make sure it's between a store and a load. Then we check that there are no intervening stores, not even aliasing ones, on the path from the forward store to the load. And then we perform the actual propagation of the stored value to the users. So let me demonstrate these last two steps on our case study. So we capture the stored value into a temporary t. Then we use this t on the next iteration instead of the load. And then we, of course, initialize this to the initial value of the recurrence outside the loop. We also need to make sure that there are no intervening stores on this path. And if you look at, we look at carefully, there is a single array that we're storing to. And as it turns out, this could actually alias the memory location that we do the forwarding on. So we need to issue one single mem check in order to make this transformation correct. So let's summarize. So let me recap loop elimination. So it's a simple pass. It's cheap because it's using already populated analysis. With loop versioning, we cover more loops. And the hope is that GVM, load-free in GVM would be simplified as a result of this because it's performing a similar optimization, but not with less loop awareness than this pass. So let's see where we are with our case study after this. So we distributed the loop, versioned it to enable distribution, vectorized the top loop, and then perform store-to-load forwarding to shorten the critical path in the bottom loop, again with the help of versioning. And with this, finally, our efforts are paying off. We get a 20 to 30% gain on Hammer, both on ARM64 and x86. But probably more importantly, we added new facilities to the loop vectorizer framework. So there's an analysis pass that is exposed now that was hidden before in the vectorizer. There's a new loop versioning utility that's used by two passes here. It's also used by the LLVM-based versioning that Ashutosh Nemet presented this afternoon. There's a new loop distribution pass and then a new loop elimination pass. So where we are currently with the implementation, so everything's committed. Loop elimination got approved, so I'm going to commit it pretty soon, in a day or two. And as the next step, what we want to look at is turn on loop distribution targeting partial vectorization by default. And then we also want to look at if there's any missed opportunity by not having full dependence analysis and the freedom to reorder in loop distribution. We also would like to acknowledge people that reviewed our patches and helped with the initial RFCs. Chandler on the unrolling stuff, Hal, Arnold, and Dan with the loop transformations. And I also would like to thank for your attention and open it up to questions.
All right, do we have any questions? Yep.
So my only real question is whether you think it would be interesting to do something more like a loop-aware GVN as kind of a generalization of the loop load elimination. I understand why loop awareness in GVN makes GVN really annoyingly complicated, but it's actually possible to phrase the loop load elimination as more of a GVN style problem within a loop, and it's not as bad.
Right. So more like partial, like extra partial.
Yeah, it's just full PRE,
Yeah.
but
Yes.
like loop aware PRE, right?
Yeah.
Like, it'd be cool to do that, especially if we actually succeed at pulling the memory SSA dependence information out of GVN and into something you can reuse.
Yep. Yeah. I mean, that's something we have. I mean, our plans for this pass, or maybe it may not be this pass exactly, but to do load-to-load, also store elimination. Actually, in this Hammer loop, there are actually redundant stores that we could pull out. It needs some versioning, some memory checks as well, but something like that. So
That'd be
definitely
totally awesome.
we keep pushing it. Yeah.
Thanks for the talk first, and I've got basically two questions, one for each part. So in the unrolling part first, it kind of looked like your heuristic is kind of re-implementing the transformations, the canonicalization we perform. Like, basically, you do exactly that. You do like partially symbolic evaluation, as far as I'm concerned. So you think that's the way we should go, like do symbolic evaluation more, or do you think we can find a simpler heuristic to figure stuff out later, maybe?
Yeah, thanks for the question, and it's actually an interesting one. If you look at what we implemented, it's only simple one, and even that code elimination is also, at least looks simple. It turns out to be more complicated than we hoped, but the interesting part is that we indeed don't want to, for example, pull SLP vectorization here. So we need to draw this borderline, which we want to kind of predict and which we don't want. And probably we still want to somehow model SLP, but that would definitely be some kind of heuristics, and that's it. So if we can to model it precisely, like in this case, it's not a big overhead. You can do it by looking just at one instruction. You don't need complicated analysis for it. So we only strive to support simple, basic, cheap optimizations, if we can. And if we can't, we can replace it with heuristics, hopefully.
Okay, thanks. And the second question is for the later part. So the loop you showed and what you said you can do and can't do. My question basically is have you tried to use Poly to do that? Because the things you said you can do and you perform at the moment, Poly should be able to do them, like at least conceptually. Sure. The things you can't do at the moment, for example, like forwarding the load to the later block and so on, something like that, and figuring out that you can split the bottom part of the whole thing because it's like kind of dependent on the induction variable. Anyway, like those two things are in Poly too, so you can do those and you can do outer loops and basically, yeah. So that's
Sure. So I haven't tried Poly, but I definitely will try it. But I think, I mean, as you saw here, we only look at the inner loop. So we're really not, I think Poly, so my opinion is that Poly would be interesting if you really have we have multiple loop nests, and it's really sort of worth going into the cost of building the models. But certainly, I think seeing where Poly would take this loop, I think it would be obviously very interesting, especially now that you guys do mem checks as well. So we basically would have we can compare things because I think we have very similar kind of facilities to do transformation. So yeah, I think I think that I would probably use it more with nests, not like inner loops, but definitely worth looking at it.
So one question, have you considered using the existing dependence analysis instead of the new analysis that you introduced? And I think one advantage is that it will handle nested loops.
Sure. So we, of course, we considered it. So I think there are some correctness problems with dependence analysis past right now. And we, of course, know that the one in the vectorizer works. And also, it's simply just, and that's one. Number two, we needed mem checks. So we basically wanted to add support for runtime alias checks. And the loop access analysis, whatever the vectorizer had, readily gave it to us. So it really, all it was is just really refactoring. So the interface was sort of more the interface that I was thinking would work more in sort of C code, like real world code.
Sure, and then, okay, just a question. This load optimization reminds me scale replacement by Steve Carr, maybe 15 years ago. So I think it's...
Yeah.
But it's maybe special case. So I guess my suggestion is to look at how it can be generalized using this scale replacement.
Sure, absolutely.
All right, I apologize, but we're out of time for questions, but I'm sure our speakers will be available to answer them after the talk or later on today. So please thank our speakers.